What if you could design a spacecraft that doesn't just go to space, but learns from it? A system that launches like a rocket, survives hypersonic re-entry, lands like an aircraft, and then flies again. That system exists. It's called the X-37B, and from an engineering standpoint, it represents a shift from, quote, mission-based spaceflight to, quote, iteration-based space R&D. This is not just a vehicle. It is an experimental platform designed to compress the cycle of innovation in space. Let's break it down layer by layer: structure, thermodynamics, propulsion, autonomy, and mission architecture. Start with the fundamental design, Payloads. Quote, most spacecraft are disposable. Once launched, they operate in orbit until failure. No physical inspection, no iterative redesign based on returned hardware. That creates a major limitation. Engineering becomes simulation-heavy instead of data-driven. The X-37B solves this by being reusable. This single decision cascades into multiple engineering advantages. You can expose materials to space radiation, vacuum, and thermal cycling, then bring them back and study real degradation. You can test electronics under true orbital conditions, not approximations. You can validate long-duration systems in actual space environments. This turns space into a laboratory, not just a destination. Structural engineering and configuration. The X-37B is essentially a scaled-down space shuttle-like configuration. But the scaling is not just about size, it fundamentally changes structural behavior. Smaller structure means lower bending moments during launch, reduced thermal gradients during re-entry, lower mass, lower inertia, lower easier control. The vehicle uses a lifting body configuration. This allows it to generate lift during re-entry without relying on large wings. Why is that important? Because large wings increase thermal load and structural complexity at hypersonic speeds. So engineers balance lift generation, thermal survivability, structural simplicity. The result is a compact, highly optimized aerodynamic form. Thermal protection system, the real battlefield. Re-entry is the most extreme phase. Velocity, Mach 25 temperature, greater than 1500 degrees Celsius environment. Plasma formation around the vehicle. At these speeds, air doesn't behave like a normal fluid. It ionizes. This creates a plasma sheath that blocks radio signals, generates intense heat flux, causes uneven thermal distribution. To survive this, the X-37B uses advanced thermal protection systems. These include high-temperature ceramic tiles, reinforced carbon-carbon composites at leading edges, insulating layers to protect internal structure. But here's the deeper engineering challenge: thermal stress. Different materials expand at different rates. If not managed properly, this creates internal stresses that can crack the structure. So, engineers must design expansion joints, material compatibility layers, heat flow pathways. This is not just about resisting heat, it's about controlling how heat moves. Guidance, navigation, and control. GNC, the X-37B is fully autonomous. No pilot, no real-time joystick control. This means the vehicle must continuously solve: where am I? Where should I go? How do I get there safely? It uses a combination of inertial measurement units, IMUs, star trackers, for precise orientation in space, GPS, during atmospheric phases. During re-entry, things get harder. Plasma blackout reduces communication. Aerodynamic forces become dominant. The vehicle transitions from orbital mechanics to fluid dynamics. This requires a hybrid control system that can handle both regimes seamlessly. Control surfaces become active only in atmosphere, elevons rudder. Before that, attitude is controlled using reaction control thrusters. The software architecture here is one of the most critical parts of the system. Failure is not an option. Propulsion system, EF efficiency over power. Unlike launch vehicles, the X-37B doesn't need high thrust, it needs precision. In orbit, it uses small rocket thrusters for orbital adjustments, station-keeping attitude control. The challenge is maximizing mission duration. Every orbital maneuver consumes propellant. So, engineers optimize delta V, budgeting, burn efficiency, mission planning trajectories. This is classical orbital mechanics combined with modern optimization algorithms. Power system, Long-duration design. One of the most interesting systems is power generation. The X-37B uses deployable solar arrays. After reaching orbit, the payload bay opens and the solar panel deploys outward. This transforms the vehicle from a compact launch configuration into an extended energy harvesting system. Energy is stored in onboard batteries and distributed across avionics payload experiments, thermal control systems. The key challenge is reliability over long durations. We are talking months or even years of continuous operation. That requires radiation-hardened electronics, fault-tolerant power distribution, thermal stability across orbital cycles, payload BAY, the core of ITS purposes. This is where the real mission happens. The payload bay allows deployment of small satellites, testing of experimental hardware, exposure of materials to space conditions, but the key advantage is return capability. Unlike satellites, the X-37B can bring payloads back. This enables post-flight analysis, microstructural changes in materials, radiation effects on electronics, performance degradation patterns. This data is extremely valuable for future spacecraft design. Aerodynamics from VACUM to atmosphere. Designing for space is one thing, designing for re-entry is another. The X-37B must operate across two completely different regimes: vacuum, orbital flight, continuum flow, atmospheric flight. During re-entry, shock waves form at the leading edges, heat flux peaks at stagnation points, stability becomes critical. The shape of the vehicle is optimized to distribute heat evenly, maintain controllability, avoid catastrophic instabilities. This is where computational fluid dynamics meets real-world testing. Autonomous landing, final phase. Landing is fully automated. The vehicle transitions from hypersonic to subsonic flight, then it aligns with the runway and lands like an aircraft. This requires precision navigation, real-time trajectory correction, robust control laws. There is no room for manual correction. Everything must work perfectly. Why this matters in key enduring perspective. The X-37B is not just a spacecraft, it is a platform for accelerating engineering cycles. Instead of design, launch, lose data, it becomes design, heats, test in space, return, space into a controlled, repeatable engineering environment. Because the future of aerospace will not be defined by single missions, it will be defined by systems that learn, adapt, and evolve with every flight.